Hello and welcome back to another lecture on the new NPTEL course on advanced plasticity of solid continua. So for the last couple of lectures we have been discussing about the strain gradient plasticity. In the last lecture we saw how the strain gradient affects through the gradient of the plastic strain and through the gradient of the hardening part of elasticity, the hardening internal variable, enter the free energy. Okay? So we also observed in the process that these gradient terms in the internal variables are purely energetic in nature, and therefore they do not affect the dissipation potential typically. That is the typical observation based on pure logic. That is that these gradients are responsible for a band formation in the plastic deformation. Right. So therefore we come back with this structure of the dissipation potential that we shared with you in the last lecture, psi dot being the time derivative of the free energy and phi the dissipation potential, and move forward. Okay. So if you now recall, we will use this dissipation the R, that is the variational functional, in two different ways. One is a local minimization, that means the minimization, let us say, at every material point. In practice it is minimization at the points of integration, that means the Gauss points in your finite element framework, which will lead you to the flow rule. That has always happened for all models, if you recall. And the other one will be taking the variation for the global functional, which will lead you to the balance laws. Right, we will do both. First do the local thing, the local minimization. The local minimization means that so basically first write the dual relation, right. So we know that x is del alpha dot phi, right. So that is basically equal to d alpha dot, because if you recall, this script d is essentially the damping, viscous damping tensor, right, associated with the rates of the internal variables that we have introduced in the last lecture. So that if you assume that this is invertible from the structure of the d that we had, please recall from the last lecture, it was invertible provided that those diagonal entries are non-zero, and therefore we have alpha dot is d inverse x, right. So now let us do the actual variational formulation. Of course by variational formulation what I mean is to find the Euler-Lagrange equations associated with R. Okay. Now of course we will deal with both the local part and the global part. So the global rate function will be what? That will be simply integral over omega. This, of course, to this you have to add this minus, this was missing, minus P external means the external power, which actually that has to be added, otherwise you won't be able to recover things properly. Okay. So this was missing, I am sorry. Okay. So that is the global rate functional. So basically it is basically the integral of this local rate functional modulo this extra addition. All right. Now now let us do things part by part. So you understand a few things here, right. So basically okay, so I will come back to a few points which probably will become clear as we go forward. So anyway, so let us now take the expression for psi dot that we already had, if you recall in the last lecture. Please go back and check that expression for psi dot which we reproduce here. Okay, this is the expression for psi dot, the derivative of the free energy. All right. Now the question is, this psi dot has to be put in that global variational functional, right, R. Let us put them back. Always actually that term actually I have not put. Let us put that. All right, P external. All right, because it should be there. Of course, when you take the variation with respect to the internal variables, P external doesn't contain any internal variables. You remember That is the reason I have not put, because when you take variation of R with respect to the internal variables, this term does not have any effect, right. So that is the reason, but it should be there. So R therefore has this expression that we have, right. So remember that the expression for phi alpha dot we already discussed. What was that? Okay, the dissipation potential term, right. So okay, so therefore the external, so separate the external power from the internal dissipation, right. So the external power is basically, you know, sigma epsilon E dot, that P external I said, right, that is here also, okay. So that is the stress power, which is thanks to the symmetry of sigma, it is just sigma inner product with grad of U dot. Now rewrite R as the R internal and added to P external, right. So P external is just this. Okay, so basically we have, let us first do with R internal, because that is the only term out of these two terms R int and P ext which will have these internal variables in it. Okay, so let us consider the thermal terms later on, because my major job, you know, even in the presence of no thermal transport, these gradient effects will be very important. So the major, you know, interest in this particular lecture is to tell you purely through these you know, these standard methodological aspects how these gradient terms are affecting the mechanics, right. So the thermal terms are extra, okay, not exactly germane to our point of consideration here. Okay, so let us proceed. That is what I actually have said, focus first on the mechanical part only, okay. Otherwise things become cluttered, more and more cluttered. So let us make use of the reduced dissipation, and you have to actually do integration by parts, if you recall, because without integration by parts you will not be able to free these rates of the internal variables from the gradient, right. So in order to be able to free them, these two, you have to push the gradient to the other part. That means this gradient has been pushed here, this gradient has been pushed here, you understand. Okay, so these are the things, and if you recall from the last lecture, these were the expressions for the two, you know, thermodynamic forces conjugate respectively to epsilon P dot and kappa dot. Okay, these two forces, this force was called x epsilon P and this force was called x kappa. Remember, these are conjugate to epsilon P dot and kappa dot respectively. So if you put together as both these forces x epsilon P and x kappa as a vector, bigger vector, right, then we basically have for R internal just this term, that is the dissipation potential, integral of the dissipation potential minus x inner product with alpha dot, that is it, dV, okay, integral. Plus of course you will be having boundary terms, but as long as we are interested in the local business, boundary terms are not important. Boundary terms will add to the boundary conditions, to the mechanics, to the governing equations, okay. So that are important only in a global perspective. Alright, so this is something that I have already told you, okay. So this is what is made clearer here. So capital X is the thermodynamic driving force for the rates of the internal variables. Now, so basically the overall integral of the local you know, functional, which is, you know, the integral of the local functional is itself called R, right. So this is now overall this, okay. This is the external power, this is the internal part, these are the thermal parts, right. Now the Euler-Lagrange equation, now you can we'll have to do separately. For example, if you now do the Euler-Lagrange, you can actually do the Euler-Lagrange equation by varying epsilon, then you will be getting basically the balance law at the you know, like divergence of sigma plus b equal to 0, that is it, you know, which actually is the standard Cauchy's local balance of the linear momentum balance. Now if you do the variation of R with respect to the internal variables rates or the internal variables basically, then you get also some extra equations, and these are called microforce balances. Why microforce? Because these actually are the equations that drive the modifications of the microstructure, okay, for which this is a continuum level, very continuum level representation. Okay, so let us derive first the microforce balances, because macroforce balance we all know, it is pretty simple thing. We can come back to it any time if we have to refresh our memory. It is the microforce balances which actually take the cake here insofar as the interest is concerned in this model of the variational calculus associated with strain gradient plasticity. So let us take variation with respect to the internal variable alpha, okay, variation of R with respect to the internal variable alpha, that is our job, and set it to 0, okay. So that is only our int internal part of R will have alpha, and therefore del R int is enough, and that has to be equal to 0, okay, and that is given here this way, okay. So del phi by del alpha dot minus there was another term x inner product alpha dot. This if you just take variation with respect to alpha dot, it is simply del alpha dot comes out and you have this. Alright, so basically what we have got now, you actually see that this is entirely arbitrary. Delta alpha dot is entirely arbitrary, so it is true for any delta alpha dot. So therefore this can be true, this statement of this whole thing becoming 0 can be true if the integrand, this part is 0 itself, okay. So that is what actually gives me del phi by del alpha dot equals x, which is basically the flow rule, which actually sometime back in the last lecture we showed you. We got it from here too, yes, x. That time I wanted to tell you this, but it was probably too early. So we have got x from two different angles. You see, they have to be consistent. X comes from that is by the the convex analysis setup, right. X comes from the derivative, basically the subgradient of phi with respect to alpha dot, that is x, that is the flow rule. In this particular case it is nothing but d alpha dot, and hence this is the flow rule. But this says, our new analysis says that x must also satisfy this, right. So this is the flow rule, So basically this consistency is very important, but we have already got an expression for x from that psi dot expression. You remember psi dot. By manipulating the psi dot expression over the entire body by doing integration by parts, we actually got an expression for x which was acting on alpha dot to produce power, right, to produce psi dot. And that x actually was, there were two parts, x epsilon p and x kappa, you remember, right, and okay. So that x is the same x. So that has two structures. One is x is del phi by del alpha dot, I mean provided it is differentiable, it is, I can write the subgradient as del phi by del alpha dot, right, no problem, right. And that gives me x equal to d alpha dot, d script d alpha dot. But x is also given by the other expression which we got some time back. I hope that I have written, yes, this was the expression for x. Remember x epsilon p was found to be equal to sigma minus divergence of L square grad epsilon p. You remember this, right? We found it. If you have forgotten it, please go back to the last lecture and refresh your memory. And similarly we found an expression for x kappa. So these two different representations of x have to be identical, correct. So put it equal to the other expression, so d alpha dot. correct, you automatically get a differential equations for this. The flow rule now becomes basically a differential equation, right, for the internal variable alpha. Why is it a differential equation? Because you see the spatial gradient of the internal variable comes here, the temporal gradient, that is the derivative of the internal variable, comes here. So basically it becomes a partial differential equation, right. So these are the two partial differential equation. This is for the epsilon p part, and this is for the kappa, the hardening internal variable part. And you see what actually is the role of sigma in the first. Sigma is, that is the stress, is acting as an external force, source term in this partial differential equation for epsilon p. Similarly, minus del W by del kappa, which is basically the hardening force, thermodynamic force associated with kappa dot, associated with the rate of hardening, is acting as a force to this partial differential equation for kappa, the internal variable. And note that in terms of the spatial derivatives, these are second order partial differential equations in epsilon p and kappa. So this is something very interesting in the sense that now we have got the flow rule as partial differential equations, not as your the standard flow rule. Okay, so basically these partial differential equations need to be solved actually, because these are no longer algebraic equations, right. Now you can actually get to the same logic. We have actually split this epsilon p and kappa as two separate identities for the same internal variable, one representing the plastic flow, the other representing the hardening part. But a short and crisper way is to treat it together and write the microforce balance in a shorter manner. I will tell you how. So it is the same thing, basically no difference, okay, but a shorter way. So psi dot you write this way, okay. Psi is a function of epsilon, alpha, grad alpha, absolute temperature, theta. Remember that, okay. Now take the time derivative. You see, you recall, right, psi equal to psi of epsilon alpha, grad alpha, theta, correct. So this is the chain rule. Now the mechanical stress is obviously by Coleman-Knoll, sigma is del psi by del epsilon, okay. The microforce or the generalized the stresses are associated with the two derivatives, because you have one derivative del psi by del alpha acting on alpha dot, and another derivative del psi by del grad alpha acting on grad alpha dot, correct. We put a minus on that so that the whole term comes in psi dot with a negative sign. That whole power term comes with a negative sign. Why negative sign? Because sigma epsilon dot is the external thing that is applied. You think of it as an application now, okay, to the from the this is a macrostructural application of force to the microstructure. That way you should think of the stress power, sigma inner product epsilon dot, okay. So this is positive. It is taken out in different forms, so that is why there are negative terms like sigma epsilon p dot and so on, other terms, right. So the whole thing should balance properly, right, including the dissipation. If you include all the effects of how this sigma epsilon dot is distributed, then it should balance. So that is why there is a minus sign, okay, you understand that, right. So now using these expressions for this these two A and B, two microforces or thermodynamic forces conjugate to alpha dot and grad alpha dot in psi dot, we get simply this sigma epsilon dot minus psi dot minus 1. This is the reduced this is the dissipation inequality, right, Clausius-Duhem inequality. In that you put this expression for psi dot, okay. So basically you see that sigma epsilon dot will cancel from psi dot, that means the external agency will go off, and then you will be getting this, simply this. This is my expression for the reduced dissipation inequality after cancelling out all the things which are okay. Now again we can actually forget about this part. This part is essentially separately greater than 0, right. So therefore it is not very useful, but the only problem is that there is a grad alpha dot here. We must remove that grad from grad alpha dot so that we can free that alpha dot completely, and that is why if you remove that grad from here, it will come here as a divergence term, right. So what you get in the process by integration by parts on this expression that I indicated earlier, you get simply this. Again this is separately 0, okay. What is important here is to understand is that this is my new thermodynamic force which is conjugate to alpha dot, correct, and that thermodynamic force by the same logic, now call it by x, okay, A minus divergence of B, which will contain essentially both x epsilon p and x kappa, this is conjugate to alpha dot. So it must satisfy the flow rule based on the convex analysis. It must satisfy this flow rule, right, because there is a phi that is there as part of this the overall potential, right. And so therefore this is basically the PD, this gives you the PD, right. A minus divergence of B is essentially equal to d alpha dot is the PD for. So d alpha dot is basically the terms containing the viscous coefficient, viscosity coefficients, or d inverse, if you take it this side, d inverse are the mobility coefficients, right, associated with this microforce balance. Of course you can write down the boundary conditions. Actually it is a very interesting exercise for you, you can actually try that, write the whole thing together including the boundary terms. I have actually dropped the boundary terms at some stage if you recall, but if you include the boundary terms then you will get not just these differential equations as microforce balances, but also the boundary conditions which supplement them so that you can actually extract a unique solution, right. This microforce, micro boundary conditions you can say. Okay, so it is a good exercise for you to try and find them out yourself, okay, so that you can actually have an overall idea of this thing by your own derivation. Okay, now the macroforce balance is a pretty simple exercise for us. Essentially this is nothing but the linear momentum balance, right. This is the same as always. So take the variation of the potential with respect to the displacement u, right. Now the only term that involves the displacement u, see that is why actually displacement is such a outside object. Outside means outside of the microstructure. Displacement is an object that is associated purely with these macrostructural aspects, that is with the it has nothing to do with the micro structural modifications. It has an external effect in the sense that it produces the force needed for that to happen, for the microstructure to change, right. The only term involving u is this, the stress power, correct, and that is simply written as a stress inner product with the gradient of delta u dot. Okay, you can forget about the symmetric part of the gradient because stress itself is symmetric. So you can actually produce that. So forget about the symmetric part. What you do is that when you integrate this, you just transfer this gradient to sigma by integration by parts. So you get the same story, we have been doing it for a long time, we will repeat this here. Okay, so this is my two terms by integration by parts. You have got the boundary term from the domain term which is here based on the arbitrariness of delta u dot, because that is an arbitrary virtual variation as long as it is kinematically admissible. right. That means as long as it satisfies the boundary conditions and it is sufficiently smooth as required by the governing equations for U, right. So, since it is otherwise arbitrary, we have just, you can include the body force. I did not put the external, so that external power will also have an extra term here, right, plus B U dot d omega. This I did not put. Okay. If you put it, you will be getting this B also. Okay. Divergence of sigma plus B equal to 0. Okay. If there is no extra body force, then B is 0. Typically the gravitational force in many problems are not important. So, B is typically 0 in many problems of interest in mechanics. From the boundary term, we extract the Neumann boundary condition. Basically this Cauchy's hypothesis, that is sigma n is the unit outward normal to the boundary, equals T, right. T, this script T is basically the applied traction on the Neumann boundary. Okay. Now, for the microforce boundary terms, we have these quantities. I asked you to actually find it yourself. Okay. That is why I did not, there is no need for me to derive it, you should do that. Okay. So, it is a pretty simple exercise, I hope you will be able to do it. Okay. So, this is the correspondent term, this is correspondent to this for the micro force case, right, for the microstructure. Right. Now, we are ready to give the summary. Okay. So, the rate functional global form is this. If you want to recover the Euler-Lagrange equation from the local form, you simply have x equals this, right, this, that is the local form. But from the global form, so basically this is nothing but this comes out to, in this particular case, d alpha dot, correct. Now, from the global form, we actually found by by taking the variation that this particular x has two representation, another representation which is given here, A minus divergence of B, we saw that, and we equated these two representations, right. And then we got the microforce balance. Essentially, this is the idea of how you exactly extract the microstructural evolution in the form of some maths by using the global local, these forms working together hand in hand. And for the other thing, the balance equation for the macroforce, the macrostructural thing, we do not need any local form. We actually always integrate this R, take the variation of this R and find it. Okay. So, these micro and macro balances are coupled, remember. Why? Because the micro balance is governed by sigma and macro balance is also governed by sigma. Remember that this part of this expression for A minus divergence of B had sigma. Okay. So, through that it is and also alpha, okay, they are connected, they are strongly coupled typically. So far we have understood, we have tried to foster an understanding of the primal formulation for strain gradient plasticity. In the next lecture we will be going for the dual formulation for strain gradient plasticity, right, and we will see what is the nature of the governing microforce balance there, right, it will be different. And the FEM implementation will require you to actually implement this strategy over a short time step from Tn to Tn plus 1, that incremental approach we will discuss, so that we can extract the tangent stiffness information. We will in some future lecture also describe the distortional plasticity, but before that we will describe the two temperature models for plasticity also. Okay, that is also a pretty important class of models for plasticity. The reasons for that I will describe in due course. And finally, I will finish this entire course with some aspects of large deformation plasticity, even though we will not be able to tell you the full details of large deformation plasticity, because it is a subject in its own right, and there is a lot of research ideas that are still to be fully completed or accomplished that way. So, the large deformation plasticity in its simplest form, I will tell you, okay, whatever is possible to be covered in this, relatively elementary course. Okay, so I will then stop here for this particular lecture, and I hope you are enjoying these the way that we have been treating this plasticity. I hope you have developed some understanding of this convex analysis based models so far, and I will see you back soon. Thank you very much for your attention.